Okay, this is part 5 of our review of radical functions, but we're actually finished with the radical function part. These last few problems are actually old problems, which will be included as review problems on the upcoming test. So in this video we will go back and remember how to use Pascal's triangle to expand expressions like x minus 3 to the 4th power. And we'll explore polynomials and figure out what the end behavior would be. And we will solve a polynomial inequality. Alright, just in case you're wondering why we went from problem number 24 straight to problem number 26. In the original version, it turned out problem number 25 was the same as 24, so we deleted it. But I didn't want to change the numbers in case somebody has the other version. Okay, problem number 26. Pascal's triangle. You can create Pascal's triangle by starting off with a tiny little pyramid of ones. So 1, 1, and 1. After that, you're going to add the two numbers together that you see. So 1 plus 1 is 2, so put a 2 on the next row. Now on the ends, it will always be 1s. So I'll put 1s like this. Okay, let's keep going. If adding these two together, I'm going to get 3. And then 2 plus 1, that's another 3. And again, on the ends, I will finish up with some 1s. Alright, and again, so 1 plus 3 is 4, 3 plus 3 is 6, and 3 plus 1 is 4. And then finish up that row with 1s. Alright, I'll just do one more row. Add these and you get 5. Add these, you get 10. Add these, you get another 10. And you get another 5 here. And finish off the row with 1s. Okay, now if you think of it this way, I'm going to show you how this triangle will give us the coefficients of the expanded form if you take a binomial and raise it to a power. Now the key is you have to understand that this first row you're always starting with x plus y to the 0 power. Alright, anything to the 0 power is 1, so that makes sense. And then after that, so this next row is what you would get for the coefficients if we did x plus y to the 1 power. And this one would be from x plus y squared. And we'd get these coefficients if we did x plus y to the 3rd power, and these would be the coefficients if we did x plus y to the 4th power, and these would be the coefficients if we had x plus y to the 5th power. And we could have kept going if we wanted to. So looking back at this problem number 26, alright, we have a binomial raised to the 4th power. So that means that we should be looking at these coefficients right here. Alright, so those coefficients are 1, 4, 6, 4, 1. So let's just copy that down. Alright, spread it out quite a bit. So that's going to be 1, 4, 6, 4, 1. And they always start off positive, so let's just put plus on all of these. Let me just double check. 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. Okay. The next thing we do, we are going to take the terms of the binomial and use them to figure out what the variables must be. So looking at this x, Alright, we're going to start off with x to the fourth power. The x is on the left, so I'm going to start off on the left with it. So I've got x to the fourth power. And then as I go to the right, I'm going to decrease by 1 degree each time. So on the next term, I'll have x to the third power, and then x squared, and then just x. And then this is like having x to the 0 power, but we don't write anything. Next, I'm going to do, let's see, should I do green? Look at this negative 3, and please treat it as a negative 3. So this negative 3 is on the right. So I'm going to start off over here with it on the right. So there's my negative 3. And again, I'm going to start off with the highest power here. So this will be negative 3 to the fourth power. But this time I'm going to go to the left, decreasing the power each time. So this will be negative 3 to the third power, and negative 3 squared, and negative 3, because that's like negative 3 to the 1 power. And then nothing here, because that would be negative 3 to the 0 power. So all we really have to do is simplify this, and we'll be done. Okay, so of course 1x to the fourth power is just x to the fourth power. So what should I do? So now here I've got 4 times negative 3. Well, that's going to be negative 12. So I can go ahead and put negative 12 x to the third power. Okay. Actually, you know what? Let me go back for a second. Before I do that, let's do all of these powers first before I get too carried away. So I'm just going to copy everything except for the green part. So I have, I'm just going to bring down my 1, my 4, my 6, my 4, and my 1. And I'm going to bring down all this pink stuff. So I have x to the fourth power, x to the third power, x squared, and x. Alright, so just focus on the green part. So negative 3 is going to stay negative 3. But here I have negative 3 squared. That's positive 9. Negative 3 to the third power is negative 27. And negative 3 to the fourth power is positive 81. So notice a couple things. If you have a negative number and you raise it to an even power, like 2 or 4, it becomes positive. If you raise a negative number to an odd power, a negative number will stay negative. Also, if you don't know these values in your head, like 3 to the third power, 3 to the fourth power, that's okay. You will be given a table like this. So 3 to the third power is 27. And here you can see that 3 to the fourth power is 81. But you will not have a TI-30XS multi-view. You will only have a 4-function calculator, so be emotionally prepared. So now we can go ahead and write the final answer. So from this term, we will have x to the fourth power. 4 times negative 3 is negative 12, so we'll have negative 12 x to the third power. 6 times 9 is 54, so we will have 54 x squared. Now, here we have 4 times negative 27. That is negative 108. So that will give us negative 108x. And then, of course, 1 times 81 is just 81. So this would be the expanded form of x minus 3 to the fourth power. Alright, for number 27, what is the end behavior of this function? Well, we memorized a couple functions, what they sort of look like, according to the degree. So for example, we know that if we have a function that is quadratic, so if we have x squared, we know that that is a parabola. Alright, and specifically we know that that's a upward facing parabola because of the way it's positive. If it was negative, like if we had negative x squared, that would be an upside down parabola, like that. But similarly, we learned that in general, when you have a cubic function, it has a shape that's similar to a capital letter N. Okay, and if we had a negative cubic function, it would be like an upside down capital letter N. This is very useful because all odd functions have the same type of end behavior. Okay, so if I have x to the 5th power or x to the 7th power as the degree, the end behavior will be the same regardless what happens in the middle. And so all of my even functions are going to work just like this one. Okay, so if I have x to the 4th power or x to the 6th power, it's still going to have this type of end behavior. So the degree, I'm going to focus right here. See the x to the 3rd power? That's the highest power. So this is cubic. So I know it's going to be an n type of shape in terms of the end behavior. Because the leading coefficient is negative, I know I should be looking at this upside down n as I picture my end behavior. So this is the model I'm going to use. So as we go to the left, the graph goes up. As we go to the right, the graph goes down. Oh Lord. 11:51. I don't know if you can hear that alarm, but that's the sound of my child getting out of bed. Let me go let her know her mistake. Okay, so as we go to the left, this is the left side right here. As x approaches negative infinity, that means as we go left. It goes up, so that would be positive infinity. This is the one that means as we go to the right, because it's as x approaches positive infinity, that's to the right. As we go to the right, it ends up going down, so that's going to be negative infinity. Okay, so that's how you can tell the end behavior without being given a graph. You can just do a little sketch of the end behavior. And again, it would work the same way if this were the 5th power or the 7th power. If it were an even, I would use one of these instead. So that was number 27. Okay, number 28. I think this is the last problem. Solve the following polynomial inequality. So we have this. Alright, let's factor it if we can. So if we factor this, okay, that means we'll have x times x, 42, that's 6 times 7. I need a positive 1 middle, so a negative 6 and a positive 7 will give me that. So there we factored it. Okay, we need to find the zeros of the equation. So if I set this equal to 0, okay, in fact maybe I'll just do it from 0 right here. If I set these equal to 0, so x minus 6 equals 0, x plus 7 equals 0, that's going to give me x equals 6 and x equals negative 7. Alright, that's important because those are the zeros of the function. That's why I set it equal to 0. So that means, okay, so I've got negative 7 and I've got 6. Okay, this is where the graph will equal 0. Now, do I want to include these values in my solution? Well, we want to know where the function is greater than or equal to 0. These are the zeros. This is where the function is equal to 0. So we want the values that are or equal to 0. So we will show these as filled in circles to show that they are included in the solution. Okay, so what we could do now is do some test values, is one way to look at it. So if we do some test values, okay, our thought process is like this. We need to check each one of these zones. So over here, I might look at x equals -8. Over here, I might look at x equals 0. Okay, that would be in here somewhere. And over here, I will look at x equals 7. Okay, and I want to find out if these values make true statements or not. Okay, now, I am going to use this version of the inequality. Put this back to an inequality again. Okay, so let's see. X minus 6 times x plus 7. I'm going to do that all 3 times. X minus 6 times x plus 7. Remember, I'm doing this out the long way in case we don't have a TI-30XS multiview to use. Alright, so if we go with the, if we try -8, then that's going to make this -8 minus 6, -8 plus 7. Okay, so that's going to make -14 times -1. So that's positive 14. Okay, so the question is that greater than or equal to 0? Well, yeah, that's positive, so yes, so that is a solution. Okay, if I do the same thing here, if I put in 0, then this will be 0 minus 6 and 0 plus 7. So that would just be -6 times 7. And that would be -42. So again, the question is that greater than or equal to 0? Well, that's a negative number, so no, that's not a solution. What if I do the 7? So that will make this 7 minus 6 and 7 plus 7. So that would make 1 times 14. So that's 14. Is that a solution? Well, we already checked it over here. Yes, that's a solution because it is greater than or equal to 0. Okay, if we were allowed to use our TI-30XS multiview, we would have typed in the equation here and just looked at the table of values to answer this question. Anyway, so the places where we got true statements, that's where the solutions are. So that means these values over here on the left are solutions. So we will go ahead and draw that in as an arrow. Over here on the right, this was a solution. That means all of these values over here are solutions. This area in the middle, 0 is not a solution. That means none of these values are solutions. So we'll just leave that empty. So this is the graph of the solution set. Let's go ahead and write the interval notation. So we'd have to do it like this. This part over here is from -infinity to -7, and we'll use a square bracket since this is a closed circle to include it. And then we'll say union, which we'll do anytime we have the two parts like this. And then this branch goes from 6 to infinity. Alright, and that is it. Okay, so this right here is the solution. Alright, so that is how you do problem number 28. And that is the end of this review. Thank goodness. I hope it was helpful. I will see you on the next video.